Y delta reduced voltage starter calculations. In this presentation, we're going to be looking at the inrush current values, starting torque, the current on the line and load side of the starter, voltage on line and load side of the starter, as well as the overload sizing for a Y delta reduced voltage starter. In order for us to accomplish these calculations, we will need to start with a standard motor and the full voltage start values. These values that we see here were calculated from a previous tutorial called full voltage starter calculations. If you're unsure how we got these values provided in red, go check out that presentation. Now, what we're looking at is this motor connected to a Y delta starter. So let's take a look at what this motor will look like when connected in start formation. When a Y delta motor is started, it is connected in star. And what this means is that the voltage applied to the motor windings will be exactly √3 of the E line value. So 600 divided by √3. Realistically, what we have is something that looks like this. Now, the starting current is going to be a little bit different. When we look at the starting current, it's actually going to be the full voltage starting current divided by 3. So 134.7 divided by 3. Now, at this point, some of you are saying, huh? That doesn't make sense. I mean, aren't we talking about √3? Isn't there a √3 three-phase correlation? And to that, I would say, yes, sort of. And so follow with me on a few slides so that we can unpack this and really understand why it is that we are dividing this value by 3. Where we're going to start is an unorthodox connection, which would be if this motor was started in delta. So if this motor was started in delta, you can see from the connections here that each one of my windings is connected across 2 conductors. It really would look like this, and we would get exactly the same full voltage starting current that we did in the original illustration, which was the full voltage started motor. Now, track with me here, 134.7 amps is the full voltage start inrush current. What would the phase value be then, the value of current that's flowing through each one of those windings? Well, the phase current would be equivalent to the line value divided by √3, and that'd be 77.76 amps, wouldn't it? Okay, so if we took that information and we said, okay, well, 77.76 amps inrush phase value. And then what we did is we said, well, what if we were to reduce the voltage across this winding to a value that's √3 less? So let's say we connected it to a line voltage of 347. Well, in that situation, √3 less voltage would render √3 less current. So 77.76 divided by √3 would give me 44.89 amps. Now here's the final image, and this is what sort of connects it all together. What if instead of a 347 volt delta system, we had again a 600 volt, but notice we've connected the windings in Y. Now each winding has that 347 volts and 44.89 amp phase. But notice it is now also the line current because we have it connected in Y. So kind of an interesting process as to why we have the currents we do and why that total inrush current is divided by 3 and not √3. If we were to take these values, go all the way down from 134.7 and divide by 3, we end up with 44.89. Well, let's take a look at this Y delta starter at run. Normally, at run, the Y delta starter will be connected in delta. And so we can see how this connection is made, same as the previous diagram. At this point, when we're in delta, we have 600 volts across each one of the individual windings. This means that the voltage applied to each motor winding is 600 volts. The current during run is then going to be the line side value 27 amps, whereas the load side value will be the FLA divided by root 3. And that's because when it's connected for run in delta, we would be seeing the phase current value, and we'll take a look at that starter as to where all of the conductors are located. Let's take a look at the torque. The torque of a Y delta motor at start will be equivalent to the T at start full voltage divided by 3. So exactly the same calculation as what we did to determine the inrush current. And as I alluded to before, root 3 less due to the voltage and also root 3 less due to the Y connection. Root 3 times root 3 equals the number 3. So we end up with 74.6 foot-pounds of torque. Well, let's take a look now at the current values that we would anticipate on both the line and the load side of this motor starter. During start, we know that the current will be, well, it's going to be the same on both sides. 44.9 amps is where we would expect to measure the current, and that current could be measured in any 6 of those load side conductors. 44.9 would also be measured on any of these 3 line side conductors. During run, we would measure 27 amps on the line side. However, because of the way that the motor is wound and because we have each of the individual conductors coming back from each winding, we would on this side see the phase current value of 15.58 amps. Well, what about the voltage then? The voltage on the line and the load side of the starter, well, for this one, it's actually quite simple. At start, well, the voltage on both the line and the load side, if we were to measure between these two conductors, would be 600 volts. And that's because, well, this starter doesn't actually reduce the voltage. It changes the orientation of the windings. During run, same thing, 600 volt and 600 volt line. Finally, what about the Y delta starter overload size? Remember that the overload is always sized based on the running current that is physically flowing through the overload heater. During running condition, there is only 3 overloads in the system, and one of these or these 3 conductors are actually connected in the phase of each one of these windings. This means that the overload size for a Y delta starter is equivalent to the FLA divided by root 3 and then multiplied by the section 28 multiplier. 27 divided by root 3 times 1.25 renders 19.48 amps. And if you wanted to visualize this a little bit better, you could draw something like this that shows the overload in the phase of each one of the windings, because this is essentially where it is. So each one of the windings has an overload connected in series with it, thus why we need to size the overloads to the phase current and not the line current.